Hi, I'm Zor. Welcome to Unizor Education. Today's lecture is called Second Order Curves, which sounds very mathematically. However, it's still part of the Physics Plus for all course, and it's actually very much related to physics. So, what's the relationship? We will talk about gravitational fields. We talked about this before, and we will have a major, I would say, lecture, which is the next one, about how objects are moving in the gravitational field. So let's just imagine, let's say, our sun as the origin of coordinates, and planets and some kind of comets or meteors, which are some of them are basically rotating around the sun, some of them are coming from outer space, and then they're basically coming into the gravitational field of the sun, most likely change their trajectory and maybe fly away again outside of the sun's gravitational field. But their trajectory when they are within the gravitational field of the sun is kind of changing along certain curve. So the point is, all these curves, our planets are moving, meteors, comets, whether they are or not rotating within the gravitational field of the sun, or just passing by, changing their trajectory because of the gravity of the sun. So all these curves, which are trajectories of these heavenly bodies, they're all second order curves. So what is second order curve? Well, second order curve is basically defined in Cartesian coordinates as the curve described by the equation where x and y participate, and the combined power of these two variables is 2. So basically, general form of the equation of the second order of two variables is this one. So this is second order, this is 1 and 1, which is second order, this is second order, this is lower the second order, obviously. So this is a general equation of the second order curve. So the point is that all the trajectories, our planets and meteors and whatever else are flying along, are described in Cartesian coordinates by this particular type of equation, with different coefficients which are dependent obviously on their initial position relative to sun at time 0, from which we start basically counting, initial velocity, and obviously the characteristics like mass of sun, mass of this particular planet or a comet, etc. So all these parameters which are given is supposed to be given, mass, another mass, position, direction of velocity, etc. They're all in these coefficients. But it's, no matter what it is, it will be the second order polynomial equals to 0, which describes x and y coordinates as functions of time, obviously. Both are functions of time. So at time 0, we define them as some initial conditions, and then this equation would describe position of these bodies, these objects, as functions of time. Okay, so this is kind of a final statement which I will make at the next lecture, which will be about the Kepler's law. Now, today I would like to remind you whatever is necessary to know about second order curves. Now, in a way, it will be basically a repetition of something which was addressed before. You see, this is still mathematics, and in the course called Math Plus for All, these curves of the second order were addressed. In particular, three different types of curves: ellipse, hyperbola, and parabola. Now, these are three different types of curves. They have different equations, second order equations, which describe them. But what's interesting is that these are the only three types which can occur in any kind of a second order curve. So if there is any second order curve which is described by this long polynomial ax squared plus etc., we can transform it, the equation we can transform into something which is equation of this or this or this in certain convenient coordinates, I would say. So let me just make a very quick recap about what these three are. First of all, the definition. The definition of ellipse is you have 2 points, given points, f1 and f2. The difference between them is 2c, and you have also a constant 2a. 2 is for convenience because the equation will contain a and c. Okay, now the sum of these two distances, pf1 plus pf2, should be equal to 2a. So ellipse is all the points on the plane, or if you wish, locus of points on the plane, which have this property. Sum of the distances, between this point and two foci is equal to 2a, constant. So what's given? 2c is given as a distance between these two foci, and 2a, which is sum of the distances from any point. And ellipse is all the points which are sum of these two distances is always 2a. Okay, that's the definition. Now, it has certain properties, ellipse, certain optical properties, for example, which I also address in the Math Plus course. Like, for instance, if you will have a light emitted from this foci to any direction, it will reflect off the curve and it will go into the second foci. Well, interesting property, and I have proved it in the Math Plus course. Anyway, it's just connection between the math and physics. So, equations which describe the ellipse is x squared divided by a squared, this is a squared, plus y squared divided by b squared equals to 1, where b squared is equal to a squared minus c squared. By the way, this distance is 2a, and this distance is 2b. Very easy to prove. This is major axis, this is minor axis, and they are related as this equation. This is the focal distance, 2c is the focal distance. Okay, also there is an equation. First of all, what kind of coordinates here? Well, this is x-axis, this is y-axis, which goes right in the middle between the two foci. So in these x and y coordinates, equation would be like this. Now, if the coordinates are different, let's say you have coordinates like here. This is x and this is y. So ellipse is kind of turned and shifted, etc. Equation would be different. but it will still be equation of the second order, but not as simple as this one, but more like that long polynomial I wrote in the very beginning. Okay, so all about ellipses. Oh yes, one more thing, polar coordinates. Okay, if you will have exactly the same ellipse with two foci, if you will have one of these foci as a polar origin of coordinates, this would be r and this would be angle phi, well, rather I would put theta, more traditionally theta. So this is an angle on which we have to turn from the base axis to direction to the point P. And r would be the distance from the origin. So in this case, origin is focus, F1. Well, then r is equal to a times 1 minus e squared divided by 1 minus e cosine of theta. And e is equal to c over a, which is less than 1. This is 2c, and this is 2a. Okay, so this is equation in polar coordinates. Now, why in this case polar coordinates would be, for our purposes, more, I would say, preferred way to describe the curve? Well, because it's more natural. You see, when you choose the some kind of coordinate system, you would like to choose it based on something convenient. And in physics, like for instance in these planets which are moving around the sun, well, what's the convenient point for a coordinate system? Well, you have to somehow put direction. You don't know where the ellipse actually is and whether it's ellipse or not ellipse. What you know is position of the sun, basically. And the sun is in the focal point, obviously. So that's why it's more convenient. I will address this a little bit more in more details later, but it's more convenient to describe the curve in the polar coordinates. And so in this case, this is the formula. Okay, let me just write this formula under ellipse, and we will go to hyperbola. So the formula is r is equal to a 1 minus e squared divided by 1 minus e cosine theta. Okay, hyperbola. Hyperbola is defined very much like ellipse with one little difference. Now, in case of ellipse, you had 2 points, which are foci, and you have this point, and you say that the pf1 plus pf2 is equal to 2a, right? That was the definition of ellipse. Okay, change this to minus. Well, probably you have to have this because the difference is maybe negative. So it's not to be negative. It's basically the same thing, except instead of sum of these two distances, you have difference between these two distances. Should be equal to constant to a. And what's interesting is that the curve would be completely different. The curve hyperbola would be like this. 2 branches. And this would be 2a, and this would be 2c. So in this case, a is less than c. Okay, now, again, it has certain physical properties, like for instance, if you have a ray of light emitted from one point, one focus, to hyperbola, it will reflect somehow, but if you will continue the reflection, it will hit another point. So kind of similar to ellipse, but in ellipse you have direct hit. And in this case, you have a hit to goes outside, but you can continue this line and it will still hit the second foci. Okay, so the definition is fine, That definition is difference between distances. Now equation also very much look alike. In Cartesian coordinates, it's this one. Again, very much like ellipse. In ellipse, you had plus here. Now the b I did not define in ellipse. B square was what, a square minus c square. In this case, b square is c square minus a square. Same thing, right? I mean, not the same thing, but similar. So this is in Cartesian system of coordinates, which is very conveniently supposed to be like this. So these are foci. So x line goes along the line connecting two foci, and the middle point between them perpendicular would be the y-axis. So in these coordinates, equation was conveniently expressed as this one. Okay, how about polar? Polar is also very much similar. It would be r is equal to a e square minus 1 divided by 1 minus e cosine theta, where e is the same c over a. In this case, c over a is less than 1, and that's why this is positive. In case of hyperbola, c is the distance between focus, and a is this. I mean 2a and 2c actually. So in this case, c is greater. So that's why if e would be greater than 1, and that's why to make it positive, the distance from polar origin of coordinates should be positive, obviously. Now, another interesting point is that in case of ellipse, when e is less than 1, this is e is greater than 1, the denominator is always positive, right? Cosine is not greater than 1, and e is less than 1. So the denominator is always positive. Numerator is also positive because e is less than 1. In this case, situation is quite different. Although numerator is definitely positive, the denominator sometimes might be positive, sometimes may be negative. Why? What happened? I mean, something is wrong here, right? Well, nothing wrong, because if this is hyperbola, it has asymptotes. And again, asymptotes are addressed in mass plus when I was talking about hyperbola. Basically, it's straight lines to which hyperbola becomes infinitesimally close. But if you will have from the foci to this direction, it will cross hyperbola. So r would be something normal. If you will go parallel or within this angle, the line will not cross hyperbola. So that's why for certain angles, if angle is kind of smaller, then the e which is greater than 1, if cosine of a smaller angle is close to 1, right? Cosine of 0 is 1, cosine of smaller angles is a little bit less than 1, but maybe not much. So this one might be actually negative, I mean the denominator. And when it's negative, you do not actually have any kind of r value. It doesn't really cross, so these points do not belong to hyperbola. That's it. Okay, so that's some kind of mathematical research of the formula. So we have hyperbola, we have ellipse, we have hyperbola, and the formula is very, very close, by the way. The polar coordinates. The Cartesian formula is also kind of close. But let's just wait for parabola. So, what parabola? So in case of ellipse and hyperbola, we had two foci, and either sum or difference of distances supposed to be equal to some constant. Now, in case of parabola, situation is slightly different. In case of parabola, we have a point, which is a focus point, and a straight line, which is directress. Okay, distance is 2c. Okay, now, parabola, by definition, is a locus of all points which are equidistant from point, focus, and line directress. So obviously midpoint would be one of those, and then from here we can go this way. This is parabola, and it goes to infinity. Now, the equation of parabola in Cartesian coordinates, which are in the middle point here, y square is equal to 4cx. That's quite different from whatever. I mean, it's still a second order curve, but it looks differently from ellipse and hyperbola. Not just, you know, one sign is changed. No, this is kind of dramatic change because there is no x square and there is an x here, even in this particular coordinate system. However, what's interesting, the polar coordinates, if you will take the focus as usually as an origin of polar coordinate and this line as a base axis, the polar coordinates would be like this: 2c divided by 1 minus cosine theta. Well, it's kind of close. It's kind of close. You see, everywhere you have the same kind of denominator. In this case, you can say it's also e, where e is equal to 1, right? So formula in denominator is very close, and that's where major dependency on the angle is, because angle is basically like an argument and r is the function, right? So it's like y and x. It's r and theta. So the dependency is very, very close, and just different constants in the top, in the numerator. And by the way, the optical property of parabola is, if you will put the ray of light here, it will always be reflected parallel to the major axis of parabola. Okay. Again, it was proven in Math Plus course, geometry, where I was discussing properties of parabola. So, this was just a repetition of something which, again, was in details presented before in a different course, but we should actually know these polar representations, because that's what we will use in the next lecture when we will talk about Kepler's law. Now, why will we use the polar coordinates? For a very simple purpose. If you don't know basically anything about the future trajectory, you see, in case of ellipse, hyperbola, and parabola, I started with definition of these curves, and since I was talking about, let's say, ellipse, I said, well, there are 2 points, and there is a property, the distance to this plus distance to this is supposed to be equal to constant. But I already have 2 points, which means I have a x-axis and I have y-axis. I already have coordinates, basically, convenient coordinates. If I have a comet coming into the solar system from outer space, what do I have? I don't have ellipse or hyperbola or parabola. I have absolutely no knowledge about what kind of trajectory will be. What I do know is I know position of the sun, which is origin of coordinate in my case, and I can talk about the radius towards from sun to the comet as a function which I would like to determine, this r basically, and I can choose some direction, basically any direction, as the basis from which I will use the angle. And so I have natural system of coordinates based on whatever I know. In case of ellipse and Cartesian coordinates, when I was describing this, I knew about two foci. In case of physical aspect of this, when I don't really know, I might assume that sun is one of the foci, and it is. But I have absolutely no idea where will be the second foci, or will it be at all, because maybe it will be a parabola and there is no second focus. So for physical purposes, polar coordinates are much more convenient because they're related to some physical characteristics of objects involved. Okay, so that's very important point, and that's why we will use polar coordinates. Now we will also use some x and y coordinates as well, but only after we have basically assigned the polar coordinates. So that's one thing which I would like to mention. And another thing is back to general equations of second order curve. If you have this equation, sorry, x, dx ey f equals to 0. If you have just polynomial of the second order. Now, why did I say that it will be only this, or this type? So, can you convert it using maybe another Cartesian system of coordinates, a simpler representation of the same curve? So this is the curve in some coordinate system. So my question is, can I change the coordinate system, change x and y coordinates to, let's say, u and v or whatever? And in those u and v coordinates, I can turn the system, I can maybe stretch a little bit or whatever. It would be one of the canonical equations. This is x squared divided by a squared plus y squared divided by b squared equals to 1. This one is a minus sign, and this one is y squared is equal to 4cx. Now, the answer is yes. Now, let me just do it in a very simple case. For example, b is equal to 0. So there is no mixed here. Then I can definitely put something like ax plus b squared plus cy plus d squared plus e equals to 0. I can convert this without the b into this very easily. If I will open all these parentheses and equate it with this one, I will find a, b, c, and d and e based on capital A, B, C, and D, right? Like, for example, this would be ax squared, which means a is supposed to be equal to a. Then it would be axb 2abx, right? So 2abx should be equal to d. But a I already know, so that gives me the b. Now, b squared would be what? ab squared. It would be combined with c, d, and e into f. So I can always convert this into this. But what does it mean? It means I have to shift my Cartesian coordinates from 0, where it is right now, to point minus b and minus d. And then I have to stretch by some coefficient one of these, which does not change the character of the curve, because the character of the ellipse would be still ellipse if I will change a and b. If this is equation, x squared divided by a squared plus b squared divided by b squared is equal to 1. If I change a and b, ellipse would be changed, but it will still be ellipse. So that's basically the point. Proportional change of x and y doesn't really change any character of the curve. So my point is that you can always find with pluses or minuses, with stretching, that this without the b would actually be converted into one of these three. By the way, one little point: if, for example, in this particular case, the Cartesian coordinate would be this, right? So if this is not equal to 0 and this is equal to 0, then it will be parabola. But if it's vice versa, it would be, if this is not equal to 0 and c is equal to 0, then it would be just a different parabola. The equation would be like this. What's the difference between these two? One parabola is going this way, another parabola is that way. Remember, y is equal to x squared. That's a parabola which you used to have as a function of as y is function of x. So it doesn't really matter, it's still the same parabola. Now, in case b is not equal to 0, there is a rotation of the coordinate system which can get rid of this. And it can be presented basically, what I did. I don't want to spend time because it's a little bit lengthy during the lecture, but I put it in writing. So as you know, all the lectures have notes. In this particular lecture, you go to unizor.com, Physics Plus, you go to Laws of Newton, and the lecture is called Second Order Curves. In that lecture, I put derivation in case b is not equal to 0, how to still convert it into one of the canonical forms by turning the coordinate system in the proper angle. Well, that's it. So my point was to say that a polar representation of any second order curve looks like this. And the next lecture I will derive that in polar coordinates trajectory would be one of these in polar coordinates, which basically proves that any trajectory of the planet or a comet or anything is one of these three types: ellipse, hyperbola, or parabola. Planets are circling around circling is not correct. It implies circle. It's not a circle. It's still ellipse, and sun is in the focal point of this ellipse, but the ellipse is very much close to these two focal points, are very close to each other. So ellipse is not like this, but it's more like this. But still there are two foci close to each other. So all planets are rotating. That's a better word than circling. Rotating around sun in ellipses. The comets which are coming and going are most likely would be hyperbolas, except in some very rare case when it would be a parabola. Okay, basically that's it for today. I suggest you to read the notes for this lecture. Again, go to unizor.com, go to Physics Plus. It's Laws of Newton, and the lecture is called Second Order Curves. And there is basically a full derivation of the fact that any polynomial can be converted into one of the canonical forms. That's it. Thanks very much, and good luck.